When you speak into your smartphone, your voice is naturally analog, but inside the phone it quickly becomes digital. Why do modern communication systems convert almost everything into digital signals? And if digital is so powerful, why do analog signals still exist in RF engineering? Understanding the difference between analog and digital communication is essential for every RF engineer. In the previous lesson, we learned that information can be transmitted as either a baseband signal or a passband signal. However, another important question remains. What form should the information itself take before transmission? Imagine recording your voice. Sound naturally changes continuously over time, making it an analog signal. Yet, when you send a voice message through your smartphone, the information is usually converted into digital data before being transmitted. This transformation occurs in almost every modern communication system. So, why does this happen? Why do engineers sometimes use continuous analog signals and other times use discrete digital data? Understanding this choice is one of the fundamental concepts in communication engineering. Analog communication transfers information using continuously varying signals. The amplitude, frequency, or phase of the signal changes smoothly, directly representing the original information. Digital communication, on the other hand, represents information using discrete values, typically binary digits or bits consisting of zeros and ones. Instead of transmitting the exact waveform, the system transmits a sequence of digital symbols that can later reconstruct the original information. The key difference is that analog signals can take infinitely many values, while digital signals use a finite set of well-defined levels. This difference greatly influences how communication systems handle noise, storage, processing, and transmission. Intuitively, imagine measuring temperature. An analog thermometer displays a continuously moving scale, allowing every tiny change to be observed. A digital thermometer samples the temperature and displays discrete numerical values. Both describe the same physical quantity, but represent it differently. Physically, consider a live radio broadcast using traditional FM radio. The microphone generates an analog audio signal which directly modulates a carrier wave. Now compare this with a smartphone call. Your voice is first converted into digital bits, compressed, protected against errors, and then transmitted using sophisticated digital modulation techniques before being reconstructed at the receiving phone. Mathematically, analog communication processes continuous time, continuous amplitude signals, while digital communication processes discrete symbols represented by binary numbers. Digital systems rely on sampling, quantization, and encoding to transform analog information into digital form. Both analog and digital communication remain extremely important in RF engineering. Analog communication is still used in applications such as FM radio, AM broadcasting, analog television archives, and certain aviation communication systems due to its simplicity and low latency. However, nearly all modern wireless technologies, including Wi-Fi, LTE, 5G, Bluetooth, GPS, satellite communication, and IoT networks, use digital communication. Digital systems offer better noise immunity, error correction, higher spectral efficiency, encryption, compression, and compatibility with computer processing. For RF engineers, both domains are essential. Although the information is usually digital, the RF hardware that generates, amplifies, filters, and radiates the signal still operates using analog electronic circuits. The comparison between analog and digital communication highlights an important fact. Modern communication systems combine the strengths of both approaches. Information is often processed digitally for accuracy and flexibility, but it must eventually pass through analog RF circuits before it can be transmitted over the air. A common misconception is that today's wireless systems are completely digital. In reality, every digital communication system contains an analog RF front-end, including oscillators, amplifiers, mixers, filters, and antennas. Digital processing and analog electronics work together to create reliable wireless communication. Now that we understand how information can be represented, the next step is to examine where that information actually travels. In the next lesson, we will explore the communication channel and discover how signals propagate from a transmitter to a receiver through different transmission media. In this lesson, we learned the fundamental differences between analog and digital communication and saw how each represents information in a unique way. We also explored why modern wireless systems rely on digital processing while still depending on analog RF hardware for signal transmission and reception. In the next lesson, we will explore the communication channel and discover how information travels between the transmitter and the receiver in real-world communication systems. If you found this useful, like the video, subscribe, and follow for the next lesson.